Welcome back to a brand new episode of Turing Complete. Hopefully we'll go through the challenges a bit faster than we did last time, but I mean, we're not all perfect, so be it. Alright. We are here now. We're in the last couple steps, so let's see how far we get through. We are doing functions now, which sounds kind of fun. Sorry. Cheers. Alright. Let's begin. This level is my second favorite pastime, converting hexadecimals to binary under time pressure. When dealing with a lot of bits, binary can become hard to read. Hexadecimal base 16 represents each combination of 4 bits as its own character. Yep. Yeah, so yeah, 0 to F. As an example where hexadecimal is much clearer, let's compare the representation of the largest 16-bit number. Binary is 1111, decimal 65535, hexadecimal FFFF. And it's basically blocks of 4, so it is not easy to tell if the binary is missing a digit or if the decimal number is up by 1. The hexadecimal, on the other hand, is immediately clear once you get used to the representation at least. Toggle the bits in the level panel so they add up to the hexadecimal number in the question. You must be level 3 to pass. Alright, what is 1? What is 2? What is 3? What is D? D is, oh god, this part is gonna take me some time. B is... C is this. 1 is this. E is, this. 16. Oh, whoops. 1, 6. That's a different number. What is 2 in binary? 3. What's 5 in binary? What is 2 in binary? 4 in binary. 3 in binary. F is all of them. 3 in binary. 2 in binary. 5. 1. E is this one, sorry. Oh, lucky click. 6 in binary. A is this. Ooh. 6. E 12. 2 F. 7. 39. 0 B 20. 2 D 5. 2 D 78. 5 O 4 2 6B 7 D is yes 38 22 66 2 C is oh no. Oh no. What is 4? What is 75? What is 17? What is C4? What is DD? Oops. Alright. We got it anyways. Very exciting. To shift a value left. To shift a value 1 left just means moving all the bits in a byte to the left by 1 position. So shift 1 would become that. Shifting 3 would become that. The task in the level is to shift the first input to the left by the value given by the second input. The second input will never exceed 7. So naturally, there is a version where we just build the circuit 7 times and like be done. That sounds not interesting, so how else can we do this? Ideally, we have a way of where left shift is not a addition, is it? No, I think addition would be cumbersome. Wait, what? Oh, it does become bigger. It is multiplication by 2. Or 4 or 6 or 8. I mean, adding kind of works. Okay, yeah, that's what we'll do. We'll just use the add tool. I think this is easiest. 2, 3, 4, 5, 6, 7, 8. No, 7. We just use 7. And we'll just add a number to itself every time. And then output it, and then we'll use some switch statements in order to get the value that we need. So we start our value off here. We pass it in, as well as it like that. Like that. And so every stage the number is going to double, which is exactly what we want. There we go. And then finally we just need to connect everything via switch statements. So like that. Maybe consistency there. And then we just need to Yeah, unplug you. Use a 3-bit decoder on the first 3 bits. And then we connect everything to the respective counter, although everything will be mirrored, kind of. Come on. There we go. Oh, no. Oh well. Like that. Like this. Like this. Oh, we need to add one more at the very end. So we need to add one more here. Not that. We need to add a switch. So we add another one. Like this. Pointing the right way. Yeah, we'll just connect all these together like this. There we go. Nope. There we go. Okay. And now we connect all of these ones together. Okay. And we just plug this into the output. Like that. Oh, wait. Addition includes overflow. I didn't think of that. Yeah, so because we are allowing overflow, that basically means when we multiply by 2, we might get some extra. Wait, do we? Hang on, let me stretch. Yeah, this coffee really is not doing it for me. I got to the bitter part where all the grains have gathered at the bottom. Ugh. Okay. I think these should be correct though. Even if you multiply by 2, this is multiplication by 2. So these should be correct. Hang on. What's the shift? Aha. Yeah. Oh, and this is still not connected. Now it's connected. There we go. Yeah, it was correct. I just forgot to connect 0. In addition to giving you a left shift component, we also had the intent create a right shift component. All we had to do was to create the mirror version of this schematic. I recommend that you add shift left and shift right to your hardware for future levels. Okay. So we can do that now. So we have a shift. Ooh. Wait, there's many versions of a shift left and shift right. No, hang on, let's go back. By which I mean let's go forward. We'll implement it when we need it. Add a RAM block. So the computer can address 256 additional bytes of memory. You will need a way to decide of which of the 256 bytes inside the RAM we're addressing. Select a register and wire it up so its value always selects the RAM address. When you later want to load and save the RAM, you will have to first copy the RAM address to this register. In this test, first copy from inputs 32 times and store these values. After you have loaded the 32 values, output them in the same order as you got them. Outputting before you have read all the inputs will fail the level. Okay. So we have RAM. There we go, look, RAM. And it does exactly the same thing. For outputs, load, save values. Wait, what? Hang on. Why do we have 4 outputs? If it reads them one at a time, then it shouldn't have an issue. I guess 4, yeah, 0 to 3 are used, so probably 4 would be the sensible one. This one right here. How do we do this? What is that? Okay, let's split it back to 8. Okay, we have to plug in. I guess we have to, like, come up with the ingenuity ourselves. We're basically designing our own program now, right? Is that what we do? I mean, it makes sense to always take what's in register 4, for instance. Or I'm so confused about the output 1 to 4 thing. What does that mean? I guess it's just okay. Let's just do it the way I think it is, and that is to just ignore output 1 to 4. Because it's not exactly clear what it does. Okay, we'll wire it up to number 4. So register 4 is that one, and we will connect this line, the always on line, to here, there, there, address would be this one. Okay. Oh wait, why is it different? The wire is different. It's green. Intriguing. Wait, hang on. The address is a 256. It should be the same color, right? Because it's 1 byte, the input. Okay, now I'm actually kind of confused. And this is also... Wait, did I take out the wrong RAM? Is there more than one RAM? No, that's the only one. Wait, so will this work? If I did, say... a bit constant. Okay, I guess it will work. Right? Yeah, they just made it randomly complicated by using a different colored wire for no reason. Okay, that's fine. So we'll connect this to this, and then we'll connect this to... Wait, that's the other thing I don't actually know. How do I load... Oh, save values there. Okay. So we'll connect this to output, which is here. And now these are stars for some reason. Okay, sure. And then I guess input to RAM? Wait, input to RAM. I already forgot the actual like structure of the program. So the first one is an opcode. 2 and 3 are arguments, and then output 4 is what was output 4 again? I don't remember. Oh, okay, no, now I remember. It's input is the number, output is another number. The final answer was the address. And then we have opcode. Okay, no, got it. So what we're doing is we need to assign a number to RAM. For now, let's just do number 8. Because I don't know what else to give it. So we'll give it the number 8. Just like that. And then that means it will read and write with the number 8. So we need to connect this to argument, well, basically the same way we did it before. We need to connect, I guess. We need to get ourselves some... Wait. Are these cables all... Wait, that's also a different color, isn't it? Okay, so I guess this just means it supports a 64-bit input, but it doesn't have to be 64-bit. It can be It can be 250 1 byte input. So that's good. That would be good. Or 8 bits. Yeah, bits, not bytes. So what we're gonna do is we are going to, I guess we'll just put 64 byte entries, maybe? I don't know. Well, no, because the switches are only for 8 bits. Okay, so we have our switches, and we're gonna plug them in. Like that. And just like in this version, we're going to say the top one is 1, and we connect it to this circuit. The bottom one is 2. Which will connect to this circuit. And now we have to gatekeep by getting this formula. So we go here. So that should be good for 1. And then for 2. Oh, wait, we need it. We need to do an equal first. Make sure they're equal before we do anything to them. There we go. And we need to put our constant symbol. Oop, we deleted it by accident. That's okay. 8 bits. Connect both of these. Just like that. Now we connect this basically the second wire to our first input. Or needs to compare with the first input. Here we go. No, I connected to the wrong place. And to connect it here. There we go. And then plug that in there. Similarly, we'll plug that here. Except here we need... Basically we need this one. Okay. And now... I think this should be set up properly, so... It should basically read from number 4 which place to go. I don't know if it wants to do 4 or 3, but oh well. Maybe it's prudent to do 4 and 5 so we can read 2 memories at the same time. But that won't do anything, would it? I don't think you can read out of RAM at the same time, which is the issue. Wait, I didn't wire these correctly. Yeah, no, I definitely didn't wire these correctly. What am I doing? Oh no. My mind is going... It's leaving me. We need to connect these to the outputs. I think. Hang on. Do we... Is it the outputs we need? Yeah, I think it's the outputs. This part... I think this part is just connected to whatever feed has all the outputs. So this one basically. There we go. I think that's more accurate. So now, yeah, it'll read 4 and then spew it out. And values that leave here. Oh wait, hang on. Maybe it should be around here. Okay. I thought there was something there. Okay, I think this should work. I hope it works. Okay. And so now what we do is if we want to save to RAM, we write the number 250. No, we write the number 8. And we make sure number 4 has what it needs. Okay, so program. What we're gonna do? Hang on, I need to. My hand's freezing. Ugh. Okay, what we need to do is we need to load stuff into the RAM. So we'll need a loop and then we'll need a countdown. I think we put the countdown in number 5. So this will read the input 32 times and output it 32 times. Is that? I think that's the number. So wait, did I actually... Wait, this... Hang on. Yeah, so I have to write a program for this. Wait, how do we write this program? I don't think I've actually written a program for this computer before. Have I? Hang on, go back, go back. No, I definitely haven't. Okay, I have to figure this out. I have to guess. Is it just, 2, 3, 4, like this? Okay, it's like that. So. Increment. So that would be add. I think 1 in this current case, so we'll define 1 to be register 5 basically. So because there really isn't a way of directly writing down 1 except by putting it in another register. So register 5 will contain number 1. Very fun. 1. Okay, reg 4. I guess reg, or maybe RAM address. That would be 4. That's 4. Okay, increment 1 RAM address. So yeah, we'll put it back to 1, we put that back to there. We need a counter to keep track of, or no we don't, we just need to check if address is a certain size. Lec. So lec is less than or equal to, I think, no, we want greater than gec. So gec is which opcode again? Gec gets sent to elu. Does elu have the instructions? Okay. Elu has, so we want greater than or equal to? Is that the one? Yes, we're greater than or equal to. So that's equal. This is less than. So that's strictly greater. That is needed. That is strictly less. That is. Is it this one? No, it's this one, right? Wait, is it? It's. No, we want strictly. We want not less than. Is the one we want. I just realized there's this random trailing wire that goes nowhere. Oh no, it goes to this. Never mind, sorry. I'm dumb. We want this one. We want the last one. The last one is 1, 2, 3, 4, 5, 6. The number 5. So it should be. No, come back. I want to program. So so Gek is number 5. And then we also turn on 32, which is this one. So we check if Gek is less than 32. We might have to store 32 somewhere. 30. Oh, we can actually just plug that in. No, we shouldn't do that. What we need is register 3, I think. I don't know. Wait, what happens if we want to get an immediate value from the program again? I don't remember what we needed. Is there schematics for this? No. Conditionals, immediate values. Oh! That would make my life a lot simpler if I remember that part. We don't need a lot of this. We can use immediate values instead. Yeah, so 1, 32. We can use one like this. This is... I think this is 1. Or maybe we do this. Yeah. 32 would be... this one. That's 32. Okay. So, and then we just need a label. We'll label this loop, first loop. Yeah, so now all we need is to set number 5 to be our counter. So number 5, it will be counter. Oh no, we're not doing a counter. We are incrementing and checking if RAM address is fine. So we'll set RAM address 0. I guess we'll put 0. 0. Yeah, like that. Was there a straight copy? I don't remember. Wide instruction. Hang on. XOR, byte constant, equality, byte XOR, unsigned less, signed less. Wide instruction, wide opcodes, immediate values, conditionals. Wait, hang on. What do I want? Yeah, there isn't just an option to not to just copy. I guess in which case we would have to either implement it ourselves or which would not be the hardest, I think. I mean, we could always just hmm. Maybe we do clear. I don't know. I keep clicking the wrong things. Oh, we're in the wrong place anyways. Let's do it the hacky way because I don't think we have a copy, which is interesting. Wait, we need a copy actually. No, screw it. We need a copy function because we need to copy things from the input. I just realized this is like very important. So we'll just need to create an opcode for copy. We'll just make it the 8th bit. If the 8th bit is on... Oh, I've actually boxed my components in. Hang on. Yeah, if it's just the 8th bit or 16th bit, I copy. No, there's. Which one should I use for copy? I'll use 16. If 16 is on, we're copying from the first argument. But then that's... Yeah, that's what we're doing. If 16 is on, we're copying from the first argument. So that basically will just take... So we'll extend this. We'll get ourselves some mux. Okay. We'll go around in a circle a bit. And I think the top value currently is the true value. So we'll go around and then int. Just like that. And now we're gonna grab the first input, which is that one. That's the first time that's ever happened. Okay, there we go. So if the input of input is this one is 16, it can guys be 16. No matter what, yeah, it's just gonna copy the first input. Okay, that's exactly what we need. Oh no. Oh no. Oh, this silly OR gate is still here. Oh, never mind, it's gone. We got rid of it. Bye-bye, shoo. Okay, so now we will just copy, if we needed to copy, which is very important. We need to copy. So now we can just copy. And I guess we just need a null. A null. Just something we can just plug in for. Okay, so now we can just do copy. Copy is going to be 116. Copy. Or set. No, let's do copy. Oh, we can have copy and set. Set 0. 0 set to the right ones. I think it's set null 0 to RAM address. Okay, then we're gonna set. Oh no, then we're gonna start the loop. And we're going to copy. So we now need input. Input is 7, I think, or 6. I don't remember. What's input again? Input is 7. I'm gonna set input to 7. Input. Copy input. Or yes, input. Wait, this doesn't work, does it? Wait, have I? What does immediate value do again? I don't remember. Oh, it uses the contents of 1 as an immediate value. Ah, okay. That's a different issue. So we're not loading it from the program. Oops, whoops. Oh, okay. Oh, no, never mind. No, now I understand. Now I understand what's going on. Okay. It's taking me some time to refresh from the previous session. Okay. And also some time to wake up a little bit, because the coffee is now kicking in. Okay. So I think, so set is going to take the first value, is it? Yeah, I have to fix all of these now. Or should I just take the first value? Yeah, so first value. And then copy. Wait, set. So set is going to take the first value, and it's going to use 16, whichever one 16 is. 16 is this one. So 0. Maybe instead of null, we'll call it 2. Yeah, sure. 2. This one doesn't matter. Actually, we'll set to also just disregard. Yeah, we'll do this. 0 should just be 0, so now we'll get rid of all these. Yeah, okay, 1 is 1. Or actually, we could just type the numbers in. We don't need these ones. Okay, 0, 32. So I can set 0 to RAM address. Copy the 16. Yeah. Oh, let's actually take... I mean, it doesn't matter. Copy input to RAM address, to RAM. RAM is 8. RAM. Okay, copy input to RAM. Increment. So... Or maybe add. Let's call it add. Add was... I don't remember. What was add again? Add is... 0. So add, we'll set this like that, and it's add 1 to RAM address. How does conditions work again? I got it, got it. We are going to do... Oh, that's the correct level. So gec, I think I got the right one. Gec, RAM address, (32). So if the RAM address is greater than or equal to 32, jump to... Oh no, if it's... No, we want the other way around. If we want it strictly less. Oh gosh, I don't remember what strictly less is. 32. This one probably? Less. That's the third one. Yeah, that's the third one. So that is 2. Less. So is that correct? Less. Yeah, less. RAM address. If the RAM address is less than 32, jump to first loop. Okay, now label second loop. Copy. Oh wait, no. Set 0 to... Do we need to copy it the other way? Oh, what was the... In the same order as we got them. Okay, that's fine. We're doing fine. So now set 0 to RAM address. Second loop. Copy RAM to output. Output is also 7. Add 1 to RAM address. Less RAM address 32. Second loop. Oh wait, we need to set this one. Okay. Okay, what went wrong? You need to read all the bytes first. Is this actually saving? It could be my architecture is wrong still, so... But I think if this works, the code should just work, so... Okay. Oh wait, these aren't even connected. Never mind. My thing is still not connected. Should I set it to constantly load? Will that break it? Probably. Let's do it anyways. Or actually, what we can do is we can just like... If we don't want to constantly have it load, we can just take an OR gate and plug it into load, which is obviously load is obviously the top one. We need to also plug in save. Save is which field? This one. So we need to grab a cable. Or let's grab a fresh one. Fresh cable. And we'll also grab this. And we'll do a quick comparison. Like this. And there we go. Now this should save properly. Okay, does it actually hang on? So level reset. 251. Hang on, the gates are... Am I completely misunderstanding what I'm supposed to do? Yeah, I think... Oh, I think my machine was just dumb. I should only be reading when I want to read. I.e. when one of these are on. Okay. Okay, that makes... I was just thinking, these are fluctuating at quite a rapid pace. Okay, so these should be loading in properly. Okay. Now, what's wrong here? Okay, the RAM address should be 0. Which is... I think I'm currently hiding parts of it with my camera. Where did I put my camera then? Okay. Time for radical change. Whoop! I'm now on the other side of the screen. I shouldn't be hiding anything anymore. Okay. So that's 6 is the counter. Copy input to RAM, yes. Okay, it runs through this part, except... Why is it doing that? What? Okay, let me reread what, Wait, why is this not working? Did I put the... No, RAM address would be correct. First loop is the jump address. We've highlighted this one, so... It should read 32 instead of cell 32. Hang on, let me double check. So... Let me skip to that line. There we go. So, the code is being outputted here. This code, so 32, is being sent out. 32 is being sent to the machine. So this is correct. Nothing is being sent here, but we don't need anything to be sent here. Okay, 6 is being sent. So these should all activate. Where's the counter? Where is counter? Is this counter? Yep, this is counter. Oh no, this is counter. Okay, this is not working. Why not working? Wait, yeah, one of them I'm not getting output. 0, 0, 0. Wait, no, it should still... hang on. Yeah, so this is 1. Wait, actually, I'm actually confused now. Okay, no, never mind, I'm less confused. 1 is being sent in. Okay, no. Got it, got it. 1 is being sent in here, 32. So these are the correct inputs to ALU. ALU is not outputting the correct output, though. Alright, let me check. 1, so with input... Oh. That might be the reason why it's not working. I am very smart. Okay, but now this is not working. What is happening? 16? Yeah. So now it's constantly writing the same value. Why is that? Okay. Copy input to RAM. Okay, looks like add 1 to RAM address is wrong. Is that not the correct code? You know why? Yes. Add 1. Okay, there we go. This should be correct now. And we need to do it both times. Okay. And there we go. There we go. Look at these. Ah, there we go. Perfect. Okay, can we speed this up? There we go. No, my gate score. Is that what those things are? I don't know what it is. All components have a delay, and in a circuit, the total delay is determined by the slowest path. This means that you normally want to put things in parallel. In this level, you must prove that you understand this concept. The delay of any component is ultimately derived from the delay of the basic gates, which have a delay of 2. Build a circuit with a delay of 6 and a gate cost of 5. Oh no. Okay, so we have a delay score of 8 and a gate score of 4. So we need to be creative. Or not creative, and we just put 2 things like this. Note, you can see the delay path by clicking the hourglass in the upper right corner. Yeah! I don't like being creative. Multiplying 2 4-bit numbers gives you an 8-bit number. Build a circuit that does this. The product of nibbles. A nibble is, by the way, 4 bits. So we just need to that's not too difficult, I think. Or is it difficult? Oh, I don't know. Wait. It could be painful. Basically, we just need to add column-wise. So. But then we have lots of carries. The issue is this: in this case, we are gonna have carries. A lot of them. So, I mean, we can connect them, maybe? Maybe. Maybe. We'll just be using a lot of adds if we do it this way. Because we'll need for each column, we'll basically need an add for each nib, for each, not just for each position, but for each potential carry. Which is a bit of a pain. What if I converted it to an 8-bit circuit and then I converted it to an 8-bit circuit and then converted it back? Oh, we need to do it anyways. Okay, that makes my life a lot easier. Okay, so that's our nibble in an 8-bit format. Now, all we need is a 0. Or I think the easiest way would be to we'll build. No, I keep building the wrong ones. We need the other one. This one. And we'll build 4 of these. Just like that. The first one connected normally. The second one will shift by 1. Wait, no, never mind. We have a shift. Never mind. I forgot we have a shift feature. We can just use it to shift. We'll still need the 0. So what we'll do is we'll use add. Actually, for the first gate it's overkill. We'll just use a mux. Connected these two. Wait, actually, maybe we put it the other side. It doesn't really matter, but I think it's cleaner if we do it the other side. There we go. So we'll either get 0, which is the default, or if this is true, we'll get 1. Now, we will need a shift. Oh, we also have a rotate, which is kind of cool. Yes, left. I think we can do them separately, so we'll need a bunch of constants for this. Shift. And the value by button that we'll need for the first one is 1. 1. Okay. Then we either have 2 values. We can either add these 2 together. Maybe this. Or we can skip it. And the value that we take is gonna be determined by mux. There we go, like that. Okay, what we might do is we might transfer them like this. And connect them like this. So into this. Okay. Leave it there for now. There we go. And the idea is we'll copy this little circuit 3 times. Or 2 more times at least. Except here we increment it by 2. And by 3. And then we'll connect all of these together. Connect these. Connect this. And this is the output. So, very simple. We stick our starting bit. And so this will basically collect all of our summons. All the things will add up. The first things we add up is if we add up just the number on its own. And we do that if we have a 1. And then we shift by 1 column, just like we would in like regular long arithmetic. We've done the 1s columns, then we do the 10s columns. We first multiply by 1. That's what this left shift does. And then we add it if we have a 1 in that column. Otherwise, if we don't, we keep going. And it should work. There we go. What you did here was actually multiply 2 4-bit numbers. We had the intern scale it up to bytes instead. Thank you. Thank you, interns. In order to cut spending, it has been decided to change the queuing system at public offices so that fewer people will go. Instead of first come first served, we're implementing a last come first served policy. Think of it as a stack of numbered slips where the citizens either put a slip on top or the bureaucrats take one off the top of the stack. We want you to implement this new system. Each tick the input will either signal push or pop. If it is push, store the value in the top stack. When it is pop, remove that value from the stack and output it. The output has an enable pin. Enable it only on pop. Wait, are we given a... input, don't pop, push the value. The only issue, we're not given like the amount of space we have, right? Are we going to be using RAM for this? I mean, I can use RAM. I'll use RAM. I'll use a RAM. It's actually not that much harder. Because we can use the counter. If we have a counter. There you go, that's a counter. I assume we're only given either push or pop. So, push. Push is load. No, push is save. Pop is load. Which we'll have to connect like this. You're gonna do this. like this. And the counter actually, we might want a buffer instead, because the counter will keep counting up. The buffer... we can add. So we'll take a buffer. We can use the add. Okay, and when either of these are on, we'll basically load and save simultaneously, I think. Where's an OR? There's an OR. So we'll load and save simultaneously. Oh, hang on. We'll connect this to the address. Okay. Turn this upside down. Load and save. Oh god, this is a little messy. Okay, the point is, when either of these are on, we'll both load and save simultaneously. And then what we're gonna do is we're gonna feed this back into itself. Except we're gonna have to also change this by 1. And the amount we change it by 1 depends on whether or not... Okay, so we're gonna have to do a mux. We'll do a mux. I'm just going to assume that only one of the operations are going to be on at a time. If both of them are on at the same time, it's going to be annoying. Yeah, actually, we can deal with... We can maybe deal with... I don't... I'll trust that not both of them will be on at the same time. If I run into errors, that's why. In which case, we want 1 if we're pushing, which is this one. So 1 if we're pushing, and -1 if we're popping. So this is popping. So that would be -1. And this one would be... What? Okay. The input is -5. Okay, let's turn it back to 250 times. Yeah, so why is it going up? Okay. What if I delayed it? Does... Maybe it doesn't work. We need to have it... you know what? we can add an extra filter at the start. Kind of like a catch-up mechanism. This catch-up mechanism will add -2 if we're popping. So this will be the correct register. Or -1? Maybe -1. Otherwise 0. And then we'll need to mux it. Actually, only if we're pushing, yeah. There we go. There we go. Look at this. Oh gosh, this circuit is gonna be used? Ugh. Your circuit has been saved to the component factory. This is not a good circuit. Oh no. Sorry, give me a moment. I need to double check that the stream is still up. Sorry, give me a moment. I need to double check. Okay, I think it's probably... Yeah, I disconnected quickly. But we're back. Okay. Welcome to the lab. Just like the component factory, this is not a normal level, but a tool. Programming on a buggy hardware is very frustrating. It is painful to suddenly be forced to reason about circuits when you're in the middle of solving a programming problem. It is tempting to apply a quick fix, so you can get back to solving the original problem, but now this quick fix broke something else in the program that used to work and so on. Therefore, when developing hardware, try to aim for 100% reliability before you start programming. This level uses programs to test the circuits. When the programs are run, this level checks if the linked components behave the way you expect. The lab has 2 extra keywords. The expect keyword is used to describe what a value a memory address should hold. Next tick. The first number after expect is the index of the linked component. The second number is the expected value. The linked component index is just the order of the components are connected up to in the program component. For example, expect 24, copy. Here the first line says we expect the second linked component to hold the value 4 after the next tick. All linked components are checked against expectation at every tick. All linked components are expected to be 0 at the start of the program, and expectation for memory components only change as you specifically change the expectation. The one exception are counters. These are naturally expected to increment each tick. The second special keyword for the lab is set input. With this, you can control the input of the computer. You can at any time also re-import example test by clicking below. Also, since you have now completed leg, I have unlocked all the 16, 32 and 64-bit components that you have in the sandbox. Cool. So there's literally nothing else to do here. I believe in my computer. It's a beautiful computer. I'm sure it's fine. For now. Let's keep going. Integer divide 2 numbers to find the quotient and the remainder. Consider the fraction 7 over 3. 3 goes into 7 2 times and 1 is left over. Here 2 is called the quotient and 1 is called the remainder. In this exercise, you are first given the numerator and then the denominator, and you are then expected to output the quotient and the remainder. I guess we're given 2 positive numbers. Okay, we'll do it. We could do it the dumb way. Let's do it the dumb way. By which I mean, we'll keep taking away until we reach a point where our program doesn't work anymore. As in, we keep taking away the bottom number away from the top number until we reach a point where the top number is less than the bottom number. That thing. That's the easiest algorithm I know, and it works. It never said that you have to make an efficient program. And I refuse to do so. So, And the good thing is we can just do it on our circuit. We don't have to implement anything else. Okay. So, input. Oh, input. We actually need to input is 7. Okay. And so is output. Okay. Now we're gonna save. I think we're gonna. We could just use register 1, 2. I mean, it doesn't really matter, does it? Okay. If we have to change something, we'll have to change something, but... Yeah, we'll save... We can save the denominator in 0 and... Or no, let's use the same style as overture. We'll save the denominator in 1 and the numerator in 2. So... The num is 1. Num is 2. We'll need a subtraction. Subtract, which is going to be this code. We'll need to test. We need a lac, I think. No, we need a strictly less. Which is going to be 32, 2, I think. So that'll test if the denominator, we need to test to see if the denominator is less than the numerator. We'll also need a counter. So we'll need the quotient, which will be register 3. And then, so we have the quotient, the remainder will be the denominator after we're done with what we're doing. So, yeah, I think we've got everything. So, we'll also need a copy, actually. Which is 60. Okay. Copy input. Oh yeah, we also need a throwaway. There we go. Copy input to denom. Copy input to num. So we have denominator and numerator. Label loop. So that will be our main loop. And we are going to let me just quickly make a set which does the exact same thing except okay, there we go. Set 0 to quotient. So that'll just make sure quotient is 0. And we will need okay. I think we'll need a second label, break. So this is loop set loop to counter. Oh yeah, we need to counter, which is 6. So we'll set loop to counter. So that'll just force counter to go back to the start. So set 0 to quotient. Right, so at the very start, we'll test less. So we want to check if the denominator is less than the num. And if so, we will jump to break. So we'll break out. And then otherwise, we sub the numerator denom. Wait, I'm mixing my terms up. The top number is the numerator and the bottom number is the denominator. Yeah, I'm getting those two mixed up. Hang on, I need to fix this. Denom. Code-wise, it doesn't make a difference, but I think it helps to keep things consistent. Okay. And then we're just gonna change these two. Okay, because if I'm looking at the circuit, I want the circuit to be correct. Okay. So subtract the denominator from the numerator. And then we'll add, so we'll add, which we will do this. Add 1 to quotient. Okay, and then if we label break, we will set copy. No, we want quotient first, so quotient to output, and we want to copy denom. No, we want to copy numerator to output. Okay, that should be correct. Okay, hang on. What are we getting? So 1 is our denominator, numerator, the bottom to denominator. Okay. Ah, yes. Once again, I've made the classic mistake. There we go. There you go. That works. Oh gosh, darn it. Do not test me. A proper one would be divide and conquer, where you test the biggest bit and you remove that. But this is the easiest implementation. In this level, you are supposed to add the stack to your computer and write a program that solves the level. When the input is 0, you should pop a value of the stack and output it. When the input is not 0, you should push it onto the stack. We need to add a stack? Okay. Well, I guess we're doing it all again. Yeah, I think that this is at the point where we probably should have made this machine a component. Then we can just surround our actual thing with the component. If you know what I mean. It would be cleaner if we have to add more to our program. Maybe I'll do it just for fun. Just as a little fun side project. fun. No, actually I do enjoy this game, which is why I'm playing it. I'm super excited. I guess the fun part would be to try to figure out a way of making it run basically anything, but probably not a thing. Okay, we'll have to basically do the same thing again here. So we'll need our stack. Where's the stack? Is it a 64-bit stack? Where's our stack? Stack. This one? Ooh, display. Ooh. Halt. Persistent memory. There's a lot of fun things, actually. Maybe over time I'll just like have fun and just like do random stuff, but where is the damn stack? Oh, it's a custom item, isn't it? There it is. That's my stack. It's definitely not difficult to use. Why is there so much stuff above the thing? Oh, because I moved everything down. Yeah. Don't worry, my stack is beautiful. Okay. Output. Pop, push. And then value. Stack. Okay. So we'll need to connect this the way we normally do it. Yeah, once again, I'm just gonna say if I get a pop and a push at the same time, I just don't care. I just can't. I cannot care. Okay, so we need to connect this bit. As per the usual, we'll just connect it to the big old register. No, we don't connect it there. We do connect. We connect it to the oh yeah, we're connected to the arithmetic unit, which is okay. Which okay, yeah, we need okay. I need to constantly remind myself how this machine works. Okay, we have our switches, just like that, and we connect them like this. The stack will have a number of 9. There we go. This is the stack. We will use equality to check if this is the correct gate. So actually we'll give myself a little bit of extra birth. Just like that. Now we put one more down there, just like that. Just like that. Okay, now we need to once again grab the gates. So we'll need a copy of this. So it's a copy of this one. This one. This one. A copy. So this one connects to the first one. The first gate. Okay. Like that. This one connects to the second one, which is... I'm gonna go on a limb and say it's probably this one. Like that. Very nice. Then we connect this one to its output, which is going to be... So the output to the first ones are here. So this one has to connect to that one right there somehow. To this cable right here. Okay, and then this one will connect to this cable right here. Okay. They are connected. The inputs are connected. Now the outputs. Oh wait, we also need to... Yeah, if either of these are true, so we'll need to branch it off this way. If either of these are true, we'll need to pop. Which is this one. Okay. Now the only other thing we need to do is connect the input, which is these ones. These components. Like that. And we only push if the final gate, which I'm sure I've got... Yeah, it's that one. Okay, I'll branch off this one. It's only getting slightly spaghettified, but I'm sure that's fine. That is very much intended. It's by design, really. We test this if it matches up with our 9 here. Like that. And we connect it to our stack. Okay. And there we go. We've connected everything together. And now it's just a simple case of programming it in. So let me get rid of these. We just need to... I think it's just a very simple task of we need to pop a value when it's 0. If it's not 0, push the value into the stack. I just realized I think my stack has undefined features. Not features, undefined behaviors. If we try to extract an element from an empty stack. That might actually break it, but it's fine, it's fine. We don't need to care. Okay. Sorry. Okay, we need to input. So we'll need input. Which is 7. And output, which is also 7. Stack is 9. Equal is 32. We'll also yeah. We'll also just we'll use that so we can just... Oh, we'll do the second one. We'll do the second one. Okay. So So this will test for equality. Equal input output stack. So a test for 0. And then a bunch of breaks. Okay, I think this should be fine. Maybe copy. We need copy again. Copy is a very useful tool. Okay. So, what's the first one? Copy. No, we need to start it with a loop. So label main loop. Okay. Oh, set. Set, which is copy, but with this set, and then we just need to throw away 1, 2. Doesn't really matter. Set. You know, let's just for the sake of it register or buffer. We'll just have a buffer, which is just going to be registered 0. Buffer or copy input to buffer. So, but okay. So then what we're going to do is we're going to do 2 labels. We're going to label equals, label, or actually I think, okay, not equals, although not equals will just do nothing. We don't even really need it. Then we're going to do set. Oh yeah, we need counter. Counter is 6. Counter. Set counter. 2. Oh wait, no. Equal. Buffer. 0. Equals. Okay. So not equals. We want to copy buffer to stack. And then set count set main loop to counter. Okay. That's that one. And then the second one we want to copy stack to output. And then we want to set main loop to counter. Okay. I think that should be fine. Unless I've messed up the behavior. I am a living legend. Nice. Next, final one for the day. Sometimes it is useful to reuse a section of code. We call these sections functions. To implement this reuse, one can jump to the beginning of the function and jump back again at the end of the function. We call jumping to the function calling the function, and jumping back from the function returning from the function. But for this section of code to actually be reusable, the return jump will have to be able to return to different locations depending on where we call the function from. We can save the counter value to register before jumping to the function and use this value when returning. However, if it's done this way, a function will not be able to call another function since this will overwrite the original return address. Say function A calls function B, which will call function C. When we want to return from C, we only need the return address from B, and B will only need the return address from A. Yeah, I'm disconnecting right now. My connection! No! Okay, hang on. I'll wait for a minute. Okay, it should be good. Say function A calls function B, who calls function C. When we want to return from C, we only need the return address from B, and B, we only need the return address for A. In general, regardless of which function we look at and how they are nested, the last return address we added is always the first one we need again. This is exactly the behavior of a stack. In this level, your task was implementing function calls and returns with the call and ret instructions. Note that when returning from a function, you should jump to the address that came after the call instruction, otherwise you will end with an infinite loop. The call instruction has to do the following: add the instruction width to the counter value and push it to the stack, jump to the function address. The ret instruction has to do the following: pop return address from the stack and jump to it. You can pass information to and from a function by saving the data to registers as normal. Also be aware of which register a function will overwrite before calling it. Budget cuts have led to cutting salaries, but now the lab assistants are on strike. You will have to self-assess in this test. This will tell us something about your honesty and maturity. Okay, yeah. This is gonna take me... This might actually take me a full hour to do. Because I would have to basically design a lot of this myself. Okay. So, this is basically, I think it's an entire different system that we would need. Well, the first thing we need to do is section off an opcode to do this. So let me just double check. What exactly we need? Yeah, so I think we have to pass around the size of the I guess in some sense. Oh. Or maybe we don't need a size. Okay. No, I think I think it's fine. Yeah, the one issue is functions is in this case we have a limited amount of space. So it's basically, I guess it doesn't exactly behave like a function. It behaves more like a like how C++ does the thing where it just copies and pastes code around the place. That's basically what this would do. Except I guess more sophisticated. Because it will do it in real time. But yeah, the one downside is that if I reuse registers across the code, it will start to overwrite values that I might need. So it's not like a pure function. The function can affect stuff outside the function. But I like my waves. Okay. So what we're gonna do, the first thing we need to do is we need to figure out what opcode to give return and call, because those are important. And how we're going to fix this. I guess we only really need the first argument, which is the place to go. So yeah, so the first thing we need to do... No, actually, because we're not even using alu in this case. Oh gosh. Yeah, this is starting to get a bit spaghetti-like. Let me just double check the opcodes that we have available. Because I actually might change some of them. It does mean that a lot of my code will break, but I'll just have to deal with it. Well, the one good thing about, I think, with copy, I basically kept it all within alu. So it just comes down to changing the code. The component of alu. But I think I might change it to... this. Just so, if I do it this way, so all my previous problems will now break. Which is unfortunate, but that's the way it is. So I'll have to retest them. And just like put a footnote. That is a different value. Oh, you know what, actually? You know what? I'm just gonna remove it completely. Because I just realized adding 0 is the same thing as copying. So actually, I could, this entire time I could have just used addition. It's less clean, but I just realized you could just do that. So really, actually don't need this. I'll just have to remember to fix it to fix it later on, but okay. We're going to basically be using 16 as a way of determining whether or not we need to do stuff. Now, basically, if 16 lights up, we are blocking this entire system. Because we just do not need, we do not need any of these things to change. The only thing we need to change is the counter. So, yeah. So what we need to do... Well, firstly, because we're connecting it to here, I think we need to first move all of these a bit further along. So maybe just like up to there. So that way we can basically go put a hard block onto this component, which will be important. So that's that component fixed. Oops. Oh, that's still connected to that one. That one. Oops. It's connected here. And then this one, we can connect it... Well, actually, we probably want to connect it here. Yeah, that's the whole point of having this barrier. Is to make sure that if we roll a certain thing, we won't. Yeah, okay, there we go. Okay, now what we're gonna do if 16 lights up, so I think we have to, yeah, we have 16. None of these pass through. So this, all of these are on switches, which means I will have to implement 4 switches. There we go. Like this. Maybe we'll have to expand this slightly. Oops. Because we are basically just not doing normal... Wait. Where did the other line go? There we go. We're doing surgery on the computer. Okay, so we're gonna expand these slightly. Okay. We might have to... Perfect. Wait, does it? Oh. Oh yeah. The opcode doesn't need to be switched. That is actually a fair point. Wait, but then what's the order of... Okay, I guess because we don't have circuit dependency, these ones will turn off first. Which is good. Well, I just realized it's entirely possible that if I do this... Yeah, 0 is getting buffer red. Maybe... I think I have to set this one to 6, actually. Because we are modifying 6 regardless, so... So this one, we'll change it quickly to a... Yeah, we'll quickly change this one to an OR. Okay, so it's going to be outputting 6, which is probably what we want. Oh, but then... No, we don't. We actually don't care about it. There you go. These ones are fine. I used the 16-bit version by accident. No 16-bits on my watch. Don't be greedy. Okay, there we go. Okay, so this should set this to 6. If 16 is on. Which is exactly what we want. Okay, so if we have yeah, we'll need the 1. The 1 is how we determine whether or not to return or to enter a call. So yeah, so 16.1 is a return, and 16.0 is just call. That's what we're gonna do. I think it makes sense for this address. Or which address? Yeah, let's put it on the final the address. So we'll still need counter. Actually we'll need to recounter. So it might be helpful. Yeah, it might be helpful to just have wait. Would it be helpful to just have 6 across the board, maybe? Instead of switches, we just set them all to 6. That. So if we set them at 6 across the board like this, I mean, other than the fact that counter is getting lots of love, it means that we will be able to read it. Is what I want to do. So now the contents of 6 will appear in its output, which is gonna be this line, which we'll need. Or I mean, we could also grab it from a different place. This one. No, we'll grab it from down there. So this is its content. To which we'll add 4. We might as well. There we go. And this guy actually, what we can do is reuse this circuit. Now that I think about it, it would have made more sense to use conditional, but I think it, just for the sake of my mind, need to use the same. Yeah, I think that's the correct circuit. Just for the sake of my mind, I think it's easier for me if I did it this way. Actually, that's correct. That's correct. So, yeah. So the actual address the call address, we'll put it in output. That makes things easier for us. Wait, no. No. Wait, this doesn't work. I think we need our own mux here. Base of 16. Because there's 2 different situations. If it's 1601 and 1600, we need to set it to different things. So I think we need to do it separately. Still makes sense to keep it as a return, but we need to keep things separate. Wait, is this the correct set? settings. No, I think this is correct. Like that. Okay, so this counter is gonna be what we push and pop, basically. So we gotta get a stack now. We're gonna get a stack. Our beautiful, beautiful stack. Value is going to be this value. Perfect. This value is wait, what is this value? Do we even care about this value? I don't think we do we? Oh, this is the actual output. Where is it? Ah! Wait, no, this is the thing we had 4 to. Yeah, this thing we actually don't care about. There we go. Then this value. So if this value is 0, we're pushing. So we need a 1-bit decoder. The left bit is push. So that's the bottom one. The top value is pop. Now, why is it going upwards? I don't know. We are setting this value to what we want the counter to be. If it's on pop, we want it to be equal to the stack. If it's on push, we want to be equal to... Oh, that's what we needed this value for. We needed this, we needed this value. That is what we're setting the counter to. Aha. So we're gonna get a mux. There we go. Okay, so that is now set to... So false is we are popping. No, we're... Okay, there we go. So now this should be sending the bottom one through. Which is push. And this circuit should work. Oh gosh. I guess now it's time to find out if it works. Okay, so the function is going to be called add 1 to 0 to reg 0. Okay, and what is this? What is it? Add reg 0 1 reg 0. Return. That's it. So let me clear out this stuff. So we're gonna have a ret. Ret is 1601. Adding is this, except we want this one, so add. Reg 0 is just the number 0. Loop. Okay. Label. Loop. Label main loop. Let's do main loop. Okay. Cat. Or is it? It doesn't matter. It doesn't matter because it's just 6. Okay, so cat is 16. I don't know what to call it, but cat. And cat is going to be add 1 to... Oh. Maybe we should call it go. Sorry. Let's call it go. Go. And then we're just going to call two dummy variables, to function. There we go. So then we can write go to function. Add 1 to reg 0. Just like that. Remove cat. And then yeah, set counter 6. Oh yeah, we need set, which we're going to set set 0 to counter. There we go. Or we are setting main loop to counter. Okay, so let's see if this works. So, we start the program. It is going up. You know what? Hang on. We need to do nested loops. Nested functions. Add what? So, new function. Label. Add 3 to reg 3. So we're gonna need reg 3. Okay. Add reg 3, 3, reg 3. Return. And so this is gonna go to function, add 3 to reg 3. Okay. It's kind of exciting. Okay. Maybe add reg 0 255 reg 0, add reg 0, 1, reg 0. So we're just gonna -1 + 1. So it jumps here. Or maybe no, add 2 to reg 0, and we're just gonna... So if it works properly, it should add 1. If it doesn't work properly, add 0. Okay. Or it adds... If it works properly, it adds 2. If it doesn't work properly, it adds 0. Okay, hang on. Start from scratch. Oh. Restart. I think our return function is not working properly. Yeah, hang on. So this line of code should never be run, basically. Let me just run 8. Yeah, hang on. This is not... So this is... Okay, so it's jumping there. Then it jumps to here. Then it returns. Okay, let's see if we can figure out what's going on. So. Oh, wait, hang on. That's an issue. I can see where it's going wrong immediately. All of this should only be working so long as yeah, I think that's probably the biggest issue right now. This should only be working when there is 16. This. Yeah, and then this. There we go. So this is only when there's a 16. Okay. And let's restart. Why is the default 16? Oh, because it's the first line of code. That makes sense. Okay. Actually, let's see. Does it work now? I think it does. There we go. I think that's successfully completed. You can trust me. I think I'm happy. I think I've completed it. It's working. At least I trust myself. I'm always right, so. Okay, and with that, look at how much we've completed. My goodness. So, with that, we've streamed for 2 hours and 40 minutes. I think it's time to end things here, folks. Thank you very much for joining me on this wonderful, wonderful stream. I hope you have a good day, and I hope you have a good rest of the week. Thank you very much, and bye-bye.